previously served as a postdoc fellow at University of Cambridge, and his area is granular mechanics and mechanics of frictional and transitional geomaterials. Similarly, further he has been working on geomechanics related problem. So now I would like to hand over session to our chair and co-chair. Please welcome, sir.
A very good evening to all. I welcome you all for this parallel session on geosynthetics engineering. I'll be glad to have wonderful papers, starting from a theme talk by Shabana Khan from Strata Geosystems India Private Limited, Mumbai. Of course, Shabana has more than 20 years of experience in geosynthetics industry. And she holds a master degree in geotechnical engineering from IIT Bombay, and of course MBA in finance from ISB Hyderabad. She is extensively involved in product development, research and development activities, and of course, along with this, design of geosynthetic products and their applications for infra projects. Friends, along with her tenure of 20 years, she has handled multiple roles and responsibilities, and currently she is handling the new product and sector development responsible in Strata Geosystems. And for the theme talk, we'll be having 15 minutes, followed by paper presentations. Over to Shabana.
Good evening, everybody. Today I'll be talking about mechanism of soil deformations and its control using geosynthetic in geotechnical and various applications. I'll be briefly covering some of the case references. We'll just touch based upon the soil deformation behavior, that how under any kind of repetitive or dynamic loading, our soil deforms, goes through the excessive settlement. There are rutting which happens, reduces the surface life, and how by using geosynthetic we can enhance its service life, avoid little bit of differential settlement, also make it more confined and robust solutions, reducing the maintenance and other things. Some of the cases we will just touch base upon where we have done these kind of an utilization of geosynthetic, mostly geocells, high strength woven geotextile, uniaxial and biaxial geogrids. The mechanism of controlling soil deformations per se, geosynthetic goes in couple of mechanistic, like a reinforcement. It provides as a tensile membrane, avoid any kind of an lateral dispersion, confine the entire gravel part. Majorly, it avoid any kind of an intermixing of two dissimilar material. Separations leads to enhance the life quite extensively. So separation and filtration becomes the major functions. In the slope stabilization as in veneer reinforcement or for a reinforced soil wall, geosynthetic product have been extensively used. This is a small table. I have just summarized it, the functions with respect to the influence on deformations. If we'll just look into the reinforcement type, it mobilizes the tensile stresses and resists soil deformations. So key property enhancement will go to the tensile strength, which controls the shear and smaller amount of differential settlement as well. The product which can be utilized for the reinforcement goes as a geocell as a reinforcing mat, not as a horizontal element, but geogrid high strength woven geotextile plays a major role in terms of avoiding the differential settlement. Stiffening, where we are improving the stiffness, providing the confinement, having certain kind of a lateral restraint. These things we can achieve it by utilizing geocell and filling it with some kind of gravel or soil, or sometimes concrete, based on the different applications. The influences, basically it will reduce rutting, avoid little bit of differential settlement, improve its bearing capacity. In the separation, non-woven geotextile plays a major role. It maintains the layer integrity. Filtration, geotextile drainage composites works very well, where we basically look into the permittivity, pine opening size, transmissivity. So these are the key properties enhances in the when we are mixing with soil. So how does it improve entire characteristic of soil to take it higher load and maintain it higher sustainability? In this, when we talk about the soil, the governing factors for us would be the lateral strain, vertical strain, and pore water pressure. We need to release the water pressure. We have to reduce some kind of a strain laterally and vertically. This geosynthetic does it by providing a tensile resistance. If I have to see the lateral strain which is happening over there, so this will stretch it as a tensile element, make and confine solutions. In the tension membrane effect, it will act as a membrane and avoid, enhance the load dispersion. We can see from the second sketches, the punching shear is being reduced, and the load is being spreaded over the larger area. So it's an tensile resistance as well as confinement effect. Apart from that, its characteristic of taking the filtration drainage effect will reduce the pore water pressure generation. With these kind of characteristic and certain parameters understanding, I will just give you the couple of case references where we have done it, like we have used it on a industrial flooring. Largely my presentation covers where we have a very high loading. First goes for the industrial flooring for a manufacturing unit. In the manufacturing unit, we all know that the huge container stacks, machines, and a lot of heavy loads come onto the flooring. The flooring has to be placed on the soil, which might be having some kind of a weak strata. Sometimes what happened that along with the weak strata, we expect the heavier loading. One unit which was in Pune, when we went ahead and found out what was the suggestions, it was a 3-meter replacement. 3-meter replacement means we are almost talking about a floor of one floor. In India, like 3.5 meter is one floor. So we're talking about taking out that much of soil, replacing it with a good soil, and dumping that soil is also one big task. So how we can reduce it? What can we do better over here so that the soil is in a position to take care of the load, as well as we can avoid the construction difficulties and other things. So here we have suggested a layer of geocells. We reduced the depth from 3 meter to 1 meter, provide the 2 layer of geogrids, which basically is a PET geogrid, and 1 layer of geocell. In this way, they were able to reduce substantial cost. Apart from that, cost is one factor. The practical difficulties were reduced quite a lot. And the product were designed, like the entire section was designed based upon the actual site conditions. Surprisingly also, the soil was not so great, so it has been considered that it's suitable for the black cotton soil also, but it has to be designed. We just cannot say that it can just replace or put it on a black cotton soil. This is one of the case. Another one is in logistic park. This was quite interesting because it had a 5 stacking of containers. So 5 stacking of containers were almost bringing out around 100 tons of load onto this flow. There was a problem regarding the soil also. Subsoil was around 7 to 8 meter riverine deposit, which basically comprises of soft clay. And there was a 3 meter of heterogeneous fill. So 2-3 problems and challenges were there here at this site. So the conventional section was around 1.325 meter, which was reduced to 450 mm. And here 2 layers of geocells were placed. Economy-wise, they might not be able to save so much of money, but bearing capacity was enhanced. They were able to put across quite a load onto this particular structure with the minimal excavation and minimal construction process. So around 15% of the cost they have saved. They have used extruded geogrids as well as geocells. A 2-layer of geocells were used. It was a very rapid installations, and differential settlements were arrested over here. Again, one of the case where we have done the strengthening of soil, improving, enhancing its bearing capacity and avoiding the differential settlement. It was for the port, but for the container parking area. And this is marine clay. So it was in proximity to the seashore. So the soil deposits was quite soft, and they were facing a problem regarding the differential settlement. So they wanted to sustain a very heavy loading of tractor and trailer without getting any kind of rutting and sustaining the maintenance over here. So they were having a huge amount of an area. The area was quite big, and the suggestion was to use the dry lean concrete. The suggestions what we have given that avoided the concrete layer entirely itself. So area was, if I'm not wrong, around 8,000 square meter, or more than that, around in a few lakh square meter. So that's how they were able to reduce quite a lot of concreting work over there, which would actually take a lot of time to install entirely. This was the section. Section also was reduced from 750 mm to 450 mm. One layer of geocells were used, and one layer of geogrid was used, and dry lean concrete was completely avoided over here. And geocell form a foundation reinforcement mat, which I have already explained that it acts as enhancing the bearing capacity as well as a load load taking care of capacity for the structure. We can see the after construction the photographs of it. On top of it, during constructions, and this was the stacking of the tractor and trailers were happening at the site. It was also having a paver block on top of it. This was very interesting, but though I didn't have much of the cases or much of the soil properties to give you a lot of inside information which we are collecting it, this particular crane pad were supposed to have a 1600 tons crane, and that required around soil bearing capacity of 300 kPa. This was very near to the sea area and a very heavy rainfall area. Subgrade was quite weak. So this is again done with, if we are looking at the overall section, it's 1.2 meter, including the geocell layer. So we could actually expect that this was asking for a lot of modifications in terms of soil. So 1600 tons crane pad, they had multiple crane pad, around 10 to 12. Likewise, they have constructed over here. So this we can see during the construction photographs of this. Similarly, one more case was done for 1,000 tons of crane capacity. This is one of it for 1,000-ton crane. So the geocells performance for these heavy loading have been going on very well and proving very well. It's a less maintenance work. We are not hearing anything from there after almost we must have installed it 4 or 5 years back. So it's going quite well here. Some of the international terminal in Myanmar, there they have used geocell as in reinforcement. This is the section for this where they were also worried about the carbon emission when we talk about geosynthetic material, because the lesser energy consumption when we use the natural material, most of the attention comes to that energy conservation. Cost saving is of course the primary factor for major contractors. In conclusion, if we have to look at it, geosynthetic products like woven geotextile, high-strength geogrids, geocells, helps in strengthening the weak ground, improve its soil-bearing capacity, quite faster construction compared to the conventional material. Energy conservation is quite a lot. We do have a lot of parameters and equations to check it out that how much carbon footprint we can reduce. Whenever we are checking it, we are at least coming 50 to 60%. So that's how I've written a figure of 70 to 80% in most of the cases for carbon footprint reduction. Of course, it minimizes the depletion of natural resources. The benefit of using these material, it's a green solutions, and rapid installation we have seen can carry a very extremely heavy machineries. There is a vertical stress dispersion at a larger depth for the weak subgrades, and marginal maintenance and enhance its life. And of course, it's a factory-made product, so quality control is quite possible compared to other solutions. And economical, we can see that, of course, nobody will come to us if we are not giving any economical and technically viable solutions. So whenever we talk about geosynthetics, so everybody has to put across some factor for the economy of it. So this is something regarding.
Very nice, Shabana. Wonderful.
Thank you, sir.
Any one or two questions? Okay. I have one or two things. First of all, I should appreciate that you have given some information regarding application part.
Yes.
With some cases, 4 cases. Can you summarize or give a glimpse of what is the bearing capacity increase you expected in the case 2, where you have gone for that 5 container stack? You said that soft clay improvement. Yeah. You maybe you said that bearing capacity increased. Yeah. From what value to what value? Even that soft clay, yeah, where the requirement is 300 kPa. What is the original bearing capacity of the soil?
So can I get you these details later, because I have to go through the papers and get you all these details. Yeah. What was the actual bearing capacity and how much it has increased? For sure, it increases by a factor of 1.5 to 2 times. Okay. But it also varies, because if I'm just giving you some factor will not help you. But yeah, some cases I can provide you. These particularly, as I mentioned, that I might need to dig in more to get more precise information.
Because that is very interesting, you know.
Yes, sir. Yes.
If at all the increase is 5%, 10%, we need not, yes, give that much of importance. As you mentioned, it is twice or something like that. It is very well appreciable.
If we basically look at the section also, it actually reduces from 1.35 to 450. Like 1.35 meter to 450 mm. So it also reducing quite substantially, but of course the factor comes, we take the hoop stresses which has been given because of the geocell confinement. So those factors we consider while analyzing the bearing capacity.
Yeah, I agree with you. In geotechnical engineering, thickness is not that much important for us. Mainly the factor, as you said, bearing capacity increase, that is very, yeah, very, thank you, Shabana.
Thank you, sir.
Okay. Sir, please. Now, on behalf of the organizers, we will present a memento to Shabana for her wonderful presentation, along with Professor Ramesh. Sure. Now it is over to Professor Ramesh in conducting the other papers, please.
So the first regular presentation will be on ground improvement and drainage solution using geosynthetic section, FNH 34, West Bengal, presented by Dr. Ratnakar Ramesh Mahajan. So since it's a normal session, try to stick to the time. The time given is about 9 minutes. 9 minutes. Thank you.
Okay, very good evening to all. I am talking of a project basically of ground improvement. This is from the east part of the country of India, and this paper is authored by my colleagues Sukriti Pandit, Saurabh Rajput, Jaluka Spadaro, Rudra, and myself. So of course, a lot of work of this paper has been done by Sukriti and Saurabh. Myself, Rudra, and Jaluka, we guided the team. This project is a part of National Highway, where it's NH 34. This NH 34 is actually from the district of Nadia, where the very soft soil terrain patch is following there. Here the challenges was low-lying areas, as well as there is a presence of water throughout the year, and being close to the river area, there was a frequent flooding which was coming. Just to give a glimpse of the site, so if you see on the left hand side, what you see is the area near the road, and on the right side, that's the pavement. You can see the area is complete green and lot of stagnant water, and this is the situation throughout the year. Prolonged water logging, of course, as well as during the flooding, which creates the conditions which are not so favorable for the pavement. Usually you need to have the subgrade of the pavement to be dry, or in case if it's wet, must be considered in the design. Here the progressive deformations that have been noticed at this location. These progressive deformations have resulted in the cracks also. So this was the problem which was required to be attended. In this project, the photographs of various locations that have been captured are put in here. So it's not really so easy site to handle. In this project, the soil investigation was carried out, and around the top 1 to 2 meter, it's a filled up soil during the construction of the highway, but rest of the area, the SPT values are ranging from 4 to 7, quite deep, plus the material present here is basically soft to firm silty clay. It was expected to have a long-term settlements here in terms of the consolidation settlements. And these are the information about the soil which is present. So it's basically, you can see highly compressible soil followed by the low compressibility. The thickness is varying from 3 meters to around 8 meters. So in this project, the contractor had a requirement to improve the road in terms of chainage 57,500 to 6,800, so almost 3.5 kilometers, 3.2 kilometers, and the solution was proposed by consultant was replacement of 1.5 meter with the rock, and then build up the pavement. In this area, the high flood level is 6.2, so almost this was expected to flood during the flooding time. And those who are aware of this state of West Bengal, you don't get the rock so easily. So contractor was having this challenge, how to solve this. Tender says rock. So they approached us. In this case, of course, then we suggested to replace the 1.5 meter of rock fill with the granular material. Probably in further slides you will get better idea. So replace the rock with the granular material, and to stiffen this granular material, placement of a high strength geogrid. However, the possibilities of subgrade getting softer because of the capillary rise was still anticipated. To counter that, we had proposed a drainage composite with impermeable layer on one side, that's a membrane, and a geotextile which is permeable on other side. So geotextile is placed on facing the pavement, whereas the geomembrane is placed at the bottom. We did the calculations, and basically we looked at two parameters. One is about settlement as well as the bearing capacity. So here the without ground improvement, the factor of safeties for bearing capacity were not so critical, but the settlements were coming as critical part of it. So these are some photographs during constructions. The first placement of a non-woven geotextile, followed by a placement of granular layer, and then the you have the placement of high strength geogrid, and most important, the placement of the drainage composite. In this project, the review was done by IIT Kharagpur, and there were a lot of discussions about how deep the stresses to be considered, because we need to understand the long-term settlements. But of course, finally we could arrive to a conclusion. This is the finished road which is being built, and you can see there is placement of the pitching on the slopes, so basically from the flood point of view. And after construction, the contractor could save substantial amount of money. Not only that, it was environment friendly. Instead of stone, we used the regular granular material, and we even taken care of the capillary rise with the geosynthetic, so which covers all the applications like reinforcement as a basal reinforcement, geotextile as a separation filter, drainage using the drainage composite. Of course, this kind of solutions are basically helping to avoid the differential settlements, distributing the load over larger area, and as I said, covering most of the let's say the functions what the geosynthetics takes care. These are some references. Thank you very much.
Okay, thank you for the presentation. Any questions from the audience? Yeah, one question.
Sir, can you please go to your table, basic characterization? Basic characterization.
Sorry?
Basic characterization, that
Okay.
table. That liquid limit, plastic limit.
Sure.
Yeah.
This one, yeah.
Yeah, let me check, sir. So based on what you have classified that CH, CI and CL.
That's basically, if you look at the plasticity index, which is 20 plus, as well as the observations from the, let me just take you back. Even we have seen the site observations in terms of the gradation also, silty clay plus
Yes.
the plasticity index, and then observations which are being informed by the contractor and the department over a period of time. That's how we arrived at that.
And with the help of that A-line, that chart.
Yeah,
plasticity chart.
basically, yeah, we know the Atterberg's limit, and from there we can understand these things. Yeah.
Yes, sir. So thank you, sir.
Thank you. Thank you.
And thank you for your wonderful presentation.
Thank you. Thank you very much.
Okay, thank
Thank
you,
you.
Dr. Ratnakar. So the next presentation will be on pull-out behavior of reinforcement and reinforced earth wall by Ankit Kumar.
Hello, good evening everyone. Today I am presenting my presentation of pull-out behavior of reinforced earth wall. This work was carried out by M.Tech student Vishnu. I am presenting on his behalf. So this will be my content, introduction. So this will be my content, introduction, objective present study, methodology, numerical modeling of geosynthetic reinforcement pull-out test, and conclusion. Introduction. RE wall is type retaining wall where the backfill soil is reinforced with suitable reinforcement to provide stability. There are two types of reinforcement, extensible and inextensible, that is used in RE wall. Internal stability analysis is done for design of reinforcement. Pull-out resistance of reinforcement is an important design considering the internal stability of RE wall. Field pull-out tests are required to check whether the required resistance is achieved in actual or not. So this is the chronology of reinforced soil wall. In India, the first reinforced soil retaining wall built in India to Ludhiana using fly ash is a backfill, height of about 9 meters. And 2006, first geogrid manufactured in India. So for motivation of present study, FHW provide guidelines for choosing peak pull-out load in lab test at load at which displacement of 20 mm at the front end for inextensible reinforcement, 15 mm at rear end for extensible reinforcement. That we are using for our study, that extensible reinforcement, if pull-out or rupture doesn't occur first. And as per ASTM D6076, a minimum 75 mm can be used for termination of lab test, but there are no clear guidelines available on determining the peak pull-out resistance in field pull-out test based on lateral wall displacement. Here we have studied the effect of surcharge, reinforcement length, stiffness on pull-out in granular soil by parametric study using Plexus 3D. So this is the numerical modeling that is done using Plexus 3D. This is the dimension of the model that has been used. So this is the properties of material used that is taken from the literature, and model that we use for studies is Moore column model. So for this model evaluation, we have taken the lab test data, and we found that 40 kN of peak pull-out load is found from both at nearly displacement of 27 mm. Initially, the difference is there is because of this in Plexus 3D we have used the Moore column model. So parametric study, we have used increase the length by 2 meter, 4, 6 meter by keeping the stiffness and surcharge constant. In the next, we are varying the stiffness and keeping length and surcharge constant. In third case, we are keeping length and stiffness constant and varying the surcharge. Here, the first is the effect of length of reinforcement. If we are increasing the length of reinforcement, we are getting the peak pull-out load is increasing. So what we found ki if we are providing the displacement given at head a 50 mm for 2 meter, 150 for 4, and 80 mm for 6 meter, the displacement observed at rear end is 21.9, 42.4, and 35.4. The head displacement required to mobilize entire length is approx 29, 109, and 251. And from that, we found the normalized head displacement of 1.45%, 2.7%, 4.1. So we can say the displacement required are much higher for a large length of investment, which may generally maybe not permit as per serviceability limits. So the pull-out design should be designed according by conducting field tests. Effect of stiffness of reinforcement. As we are increasing the stiffness, there is no change in the peak pull-out load, but the head displacement required at peak load is decreasing if you are increasing the stiffness. So here also we found the normalized head displacement for mobilization of entire length is decreasing if you are increasing the stiffness of the reinforcement. So we can say that the stiffness of reinforcement affects the displacement required for mobilization of entire pull-out resistance, whereas the peak pull-out is almost constant with variation in stiffness. Next is the effect of surcharge. If we are increasing the surcharge, so we observe the peak pull-out load as well as the head displacement, both are increasing. And we found that the normalized head displacement for mobilization of entire length is around 1.45%, 1.55%, and 1.65% for 20 kPa, 60 kPa, and 100 kPa of surcharge. This is because as the surcharge increases, the shear strength of interface increases, will leads to increase in the pull-out resistance. So this will be the conclusion. With increase in the length of reinforcement from 2 to 6 meter, the peak pull-out load increase and normalized displacement for mobilization of length increase from 1.4 to 4.8%. For higher length of 6 meter, displacement required to mobilize maximum pull-out resistance is even higher in the range of 250 mm, which may not be satisfactory in terms of serviceability. The peak pull-out load is almost constant, and normal displacement for mobilization of entire length decreased from 1.8 to 1.2, while increasing the stiffness of reinforcement from 4,000 to 6,000 kilonewton per meter. With increase in surcharge from 20 kPa to 100 kPa, the peak pull-out load increase and normal displacement to mobilize entire length increase from 1.45 to 1.6%. So this is reference. Thank you.
Thank you, Ankit. Any questions?
I have something. If you go to conclusions,
Yes.
you are having an increase from 2 to 6 meters, that is almost 200 times increase, where the increase in the pull-out load is only 2 to 3%. Is it viable in terms of geotechnical aspects to increase that much length where the increase is?
No, I already told you it's not limited around considering the serviceability criteria. For that, we have to do field pull-out test. It's failing. It's already told here. Ki displacement required much higher for a larger length of reinforcement, which generally may not be permitted as per serviceability limits. So pull-out design should be done according by conducting field test.
Okay.
And last question, yeah.
Can you please go to your title page? Title page.
Yes.
So for this you are using that computer code Plexus?
Yes.
Plexus
Yes.
2D, 3D, 1D?
3D. 3D.
3D. So is it a FEM model or FD model?
FEM model.
FEM model. And I saw you are mentioning like stiffness, that word. So I have something to ask you about the basics. Can you define stiffness? What do you mean by stiffness?
Stiffness, it's like how you asking?
Yeah? What do you mean by stiffness? You are giving some value.
Yes, like
So can
if
you define
if we have length, if we divide by the thickness, so we are getting the length of reinforcement, whatever we have. If we're dividing the thickness, that we're getting stiffness.
Length.
No, sorry, load by thickness.
It's okay. I think we can discuss.
So basically, this work was not carried out by me. It's carried out by some MTech student. I'm presenting on his behalf.
Okay, but
Okay.
Thank you for a nice presentation.
Thank you, Ankit. The next presentation is on numerical analysis of geograde reinforced soil walls subjected to pseudostatic seismic loading by Dr. Saugata.
Good afternoon, everyone. I am Saugata Mukherjee. Currently, I am an assistant professor at IIT Madras. So, in next few minutes, I'll take you through a small part of my postdoctoral research work carried out at IIT Bombay. So, the topic of my research is numerical analysis of geogrid reinforced soil walls subjected to pseudostatic seismic loading. So, I need not say much about the basics of RE walls because I hope you all have seen this kind of structures nowadays. So, but I should point out the three critical components of a RE wall. So, there is of course a panel which is holding the soil in its place. Then there is the backfill soil which is being retained, and of course there is a reinforcing element which holds the soil and the wall in place through its interface friction and tensile strength. So, in the current design, what we do is we calculate what are the pressures exerted on the wall, and we try to calculate a factor of safety, and we see whether it is satisfying the factor of safety criteria of 1.5 or not. So that is the basic design. Whereas in earthquake, the design it should not be done based on only the ultimate limit state of factor of safety. So the more severe thing is the wall deformation. So, but still what we are doing is we are still calculating what are the additional earthquake pressure acting on the wall, and we try to do the design based on that additional dynamic pressure. So first I'll take you through some case studies. So these figures were taken from the literature which was reported in the literature after the GG earthquake in Japan. So as you can see that the wall is standing after the earthquake, the building is still there, whereas the wall has deformed. So here is a closer look. So the wall has deformed outward. In fact, the modular blocks have opened. And in another case, the road is there. The vehicle is moving on the wall. Yeah, the wall has deformed. And sometimes the blocks open up, sometimes the blocks go away from the wall. So these are the problems. So currently, there are no guidelines on the allowable deformation of the wall. So during seismic conditions, so the current design, they don't talk about the seismic deformation of the wall. So the allowable limits range from 0.67% to 4% depending upon the design guidelines. Suppose you are going on a road and you see the wall has deformed, but the wall is standing. Will you be able, would you like to go on the road? No, right? You will be afraid whether the wall will stand or it will collapse. So that is a major criteria for seismic loading. So my research area focuses on the deformation of the wall after the earthquake has happened. So in this part, I have done some numerical modeling where the earthquake was applied using pseudostatic coefficients. And so coming to the numerical analysis, so we have taken the famous Bathurst wall that was physically modeled in Royal Military College, Canada. So the wall has a height of 3.6 meter and it has a width of 5.65 meter with reinforcements placed at a vertical spacing of 0.6 meter. So we simulated the same wall in FLAC 2D, and And here are the soil properties, which have a unit weight of 16.8 kilonewton and a friction angle of 44 degrees. So we modeled the same thing in FLAC, and we calculated the strains and the wall deformations. So you can see that we got almost similar kind of wall deformations as well as the reinforcement strains, and they match with the measured values in the laboratory. So with this model, we did some parametric analysis by applying pseudostatic earthquake load, and we calculated different quantities. So first, you were seeing the inclination of the wedge, that is the failure wedge. So the inclination of the failure wedge has an important contribution in the stability. So if the inclination of the wedge is more, the failure wedge volume will be less, so the pressure exerted on the wall will be less. At the same time, if the inclination is less, the volume of the soil inside the wedge will be more, and the pressure exerted on the wall will be more. So therefore, the deformation will be more. So we have seen that there are some Mononobe-Okabe analytical formulations which gives you the inclination of the wedge failure. And from the numerical analysis, what we have found that the analytical formulations try to overpredict the inclination angle. So in that way, the analytical solution will give you a smaller wedge volume, and it will lead to a unsafe design. So similar to the wedge inclination angle, the reinforcement length beyond the failure surface, that is the anchored reinforcement length, the requirement of the reinforcement length is also underpredicted by the analytical results. So which also leads to an unsafe design of the wall. So here you can see the wall deformation with increased earthquake loading. So as you can see that initially during the static condition or even at lower values of the pseudostatic earthquake loading, the wall is bulging, and you can see the maximum wall deformation at around 0.6 H or so. But whereas when the earthquake force is increasing, you will see that the wall is rotating. The base is almost at its place, and the top of the wall is moving away. So it will have a rotational kind of movement. So similarly, we have seen that the reinforcement strengths, which are almost less than 1% under the static conditions, it will increase, and it can reach even up to 5% under seismic conditions, and in some cases it can even go to 13%. So similarly, the tensile force in the reinforcement will also increase, and you can see that with increased seismic intensity, the magnification factor can go up to even 30-35. And the maximum magnification is observed at the top of the wall, where the wall will have the maximum deformation. So after that, we have done some parametric analysis by varying some parameters, and our objective was to see whether the deformations could be reduced by some parametric adjustments. So the first one was by changing the reinforcement stiffness, and we have seen that the increasing reinforcement stiffness of course have a positive effect on the wall deformation. And you can see that with increase in the coefficient, the reduction in the wall deformation is linear. And at the same time, you will have a static, in the static case also, you will have a reduction in the wall deformation with increased reinforcement stiffness. And even the percentage reduction could be even up to 60% at seismic condition. So the next one was increasing the reinforcement length, and we have doubled the reinforcement length in stages. That is, first we have doubled the length in the top layer, then in the next case in next 2 layers. Likewise we did for the top 4 layers. And what we have observed that only for the top 2 layers, that is a height of 1/3 of the wall, it is only beneficial to increase the reinforcement length. And after that, even if you increase the reinforcement length, it will have very less effect on the wall deformation. So that is not beneficial. And another crucial observation which was made is that you can see from the percentage reduction that there is almost 0 reduction in the wall deformation up to a earthquake coefficient kh equals to 0.2 G. It is only beyond 0.2 G, that is very intensive earthquake, the reduction will happen. So the final one is on the reduction of the reinforcement vertical spacing. So here we can see that it increases, the percentage reduction increases with increase in the seismic load, and of course even at static condition also you will have some reduction. And one more observation we made is that it has the highest benefit at the top of the wall, that is where the wall is moving away. So with this, I'll summarize my observations. So what we have seen that the analytical solutions tend to overestimate the failure plane inclination, which is not a good thing. It may lead to unsafe design. Then we have seen that there is a rotational type of failure for these segmental block walls, whereas we have also done some experimental studies where you have seen that if you are having a panel type of wall, you will have the maximum deformation even under earthquake condition also. The maximum deformation will come almost at 0.6H or 0.5H. So then we have also seen that under earthquake condition, the maximum deformation is at the top. And of course, we have seen that there are influences of the parameters, that is the reinforcement spacing, reinforcement length, and also the stiffness, where the reinforcement length is, increasing the reinforcement length is only beneficial for the top 1/3 height of the wall. So that's all. Thank you.
Thank you, Dr. Saudin.
Any question?
Yeah, just one question.
So thank you, sir, for
Yeah,
your
thank you.
nice presentation. So I have something to know about basic regarding coefficient of earth pressure.
Earth,
Coefficient
earth
of
pressure
earth
or,
pressure.
okay. The ratio between the horizontal and vertical pressure. Active, passive, and that under at rest. Ascending order.
Yeah.
So, active, rest, passive.
Okay. Any formulation like
Sorry.
active Ka equal to in terms of phi?
1 minus sin phi by 1 plus sin phi.
Sir, excuse me. I think we can discuss it later. Thanks, Dr. Saudin.
Okay, thank you.
Thank you. Thank you, sir. Wonderful.
So the next presentation is on geosynthetic reinforced soil wall with geocell fascia by Rizwan Ahmad.
You have some issue?
Good evening, everyone. My name is Rizwan Ahmad. I am a geotechnical engineer, and I am working as a assistant manager technical development at Strata Geosystems. So, first of all, thank you all for having me here. So, my paper presentation here is more of a case study of a project which we executed at a mining site for crusher wall. So, these are the contents of my presentation. So we'll have just a project overview first. So we basically constructed a 8.2 meter high reinforced soil wall at a mining site in Odisha, Bhadrak. So this structure stands a little different from conventional RCC structure and block or panel fascia, because here we use geocell material as a fascia element, basically. And the ground was consist of a soft soil, so improvement was also required there. So we provided basal reinforcement for ground improvement. If you see, this is the plan of the project. Basically here, this is the ramp wall, and the vehicle will go from here to this ground hopper and will topple the material there, and then here in elevation you can have a better overview here. So this is how it will be built. Now there were challenges actually to execute this project. First thing, the clay was the soil was consist of soft clay, high swelling index and low bearing capacity. And since the mining industry is a very resource intensive industry, so they could not afford to delay in the construction period, so they were not ready with this reinforced conventional RCC structures. So fast track construction was required, and this falls in seismic zone 4, and the groundwater table was at shallow depth. So all these challenges were to be taken care of, and it has to be delivered fast. So we went with geosynthetic reinforced soil wall with geocellage fascia. Since it is pre-manufactured, so there is no need for casting yard or anything as such. It can be transported easily and laid fast. This is flexible, and it will be better fit in seismic condition. It is easy in handling, and as I said, key RCC structures may take more time. So now these are the wall components basically. Here you can see these are the geogrids, and 3 pockets of geocell were used, and then that part is the backfill. Now the design approach was used the same as we use for the block fascia or panel fascia, BS 8006, FSW NHI 043 for seismic checks. This is allowable stress design, and then more guidelines were also incorporated. And basically, as usual, we do the checks for external stability, internal stability, and seismic stability. So if I talk about external stability, we do the checks for base sliding, overturning, bearing capacity, and global stability. These factors must be taken into account while designing our structure. Now when we talk about internal stability, we must make sure that our structure is safe against rupture, pull out, and internal sliding. And since the structure falls in seismic zone 4, we must also make sure whether it is safe in that condition also. So the seismic condition were also checked for both external and internal stability. Now this is the wall geometry, where the maximum height was 8.2 meter, 1 meter was the embedded length, and all those criteria. And these are the loads, the dead load, vehicle load, and these are the fill properties which were considered for designing the structure. And this is the design section. So now this was the design part of the structure. Now comes the bearing capacity thing. So if I talk about the unreinforced or existing section first, so these are the soil profile there. The up to 5 meter it will consist of a sandy silty clay with SPTN value of 5 and 8. And the factored bearing pressure which was coming at the base due to the proposed structure was 446 kilopascal. And the existing bearing capacity, when we calculated, it was around 230 kPa. So it was needed to be improved. And other than that, we need to also make sure whether the structure is safe in rotational and translational stability. So this was checked in the RACER software. For unreinforced section only, we checked it first. So these are the soil property without any improvement first. So, and these are the failure circle. So here when we checked, so as per the factor of safety required as per the guidelines is 1.2 and 1.3 and 1.1 for the static and seismic condition respectively, but it came out to be 0.89 and 0.84. So this was not safe in rotational as well as in translational stability also it was not safe in seismic condition. So we came up with basal reinforcement. If we talk about conventional approach, there was this provision to remove the 3 meter depth of soil, and 1 meter is embedded depth. So altogether 4 meter of soil was needed to be excavated, which is the tedious task because the 4.3 meter at 4.3 meter depth, the groundwater table was encountered. So sometime it would be a tedious task to take that much of soil and then dump it somewhere and then start your construction. So the proposed solution was we used the 2 layer of geocell and 1 layer of high strength woven geotextile, and thus we could make it at 1.5 meter depth excavation only, like 1.5 meter of excavation was required, and then 2 layer of geocell and 1 layer of high strength woven geotextile was applied. Now this is the method which we taken into account by Bathurst and and Karpurapu, where the apparent cohesion comes into the picture when we use geocell and infill the material in it. So the apparent cohesion increased by delta sigma 3 by 2 tan 45 plus 5 by 2. So if I talk about the unfactored bearing pressure at the base was 297 kPa, so the apparent cohesion basically was 128. Earlier when the soil was unreinforced, the apparent cohesion was, I'll show you, it was here you can see this 32.7 and 52.3. But after incorporating geocell, it increased to 128.2 kPa. Now this will be incorporated in bearing capacity and the global stability as well. So 2 layers of geocell was provided. So altogether 300 mm of layer was reinforced using geocell material. This is the mechanism basically. Here you can see this is the sigma 3 and sigma 1. And this dotted line is the failure envelope Mohr circle for reinforced section basically. So this CR here you can see, this is the apparent cohesion which will come into picture after applying the geocell. Now that apparent cohesion, increase in apparent cohesion, we incorporated in our global stability failure as well. Here in this highlighted box you can see that. Now again for reinforced section, all the global stability failures criteria was checked, and here you can see the factor of safety was improved after reinforcing, and it was safe as per the guideline given by BS and FSWA.
Can you please wind up?
Yes. So this is the construction methodology. First the foundation preparation was done. 2 layers of geocell and 1 layer of high strength woven geotextile was placed. And then this was the infilling, where the first pocket of the geocell was filled with concrete, and then other 2 pockets was filled with gravel. And then the layer of geogrid will come, and this subsequently will carry up to the required length of the wall. And this is the backfilling and compaction, and this is the wall facing and finishing. So if I talk about the conclusion, the using of geocell enables the rapid installation, proven stability as per the code, FSW and BS, and using basal reinforcement, it enhances the ground performance as well. That's all. Thank you.
Thank you. Any questions? One question, yeah. A lot of questions.
Hello. It was a nice work what you observed and presented you well. So I have a little bit doubts, like you have proposed this bearing capacity calculations based on the SEER criteria only. Have you checked about the allowable settlement criteria, and have you estimated the settlement before and after?
Yeah, actually I have not put it here maybe, but yeah, it was checked. We will check for both bearing capacity and settlement. The allowable settlement in case of reinforced soil wall is, if I'm not wrong, is 100 mm. It must not be more than that, but we do check that. Maybe I have missed it here, but yeah, that must be taken care actually.
Yeah, but just rough calculations, I just check it, because your soft strata is up to something 5 meter over there, 5 to 6 meter top. Even we consider 250 kPa of the loading, what you are showing there, 230 kPa loading, additional to the your live load also. It's shooting higher than what allowable is there. It's somewhat 150 or 200.
Yeah.
But your like entire presentation as well as paper seems to be, you ensure only based on SEER criteria and factor of safety like a global. But I think you have not noticed regarding the settlement.
Okay, so actually here if you see the soil was replaced 1.5 meter. Still we have used the 2 layer of geocell and 1 layer of high strength woven geotextile, but the soil was replaced 1.5 meter from top. And once we use the geocell, it enables the stress dispersion basically. There is one paper of Sita Ram, and then other Aveshani and NATO paper is also there, which people are following. Anyway, we can discuss it in later.
Sure,
but yeah, settlement thing. Yeah.
Thank you, Rizwan.
Thank you. Thank you.
The next presentation is on pull-out modeling of modified coir geotextile soil interaction by Ms. Aarti.
Good evening, everyone. I am Aarti from IIT Palakkad. I will be presenting on pull-out modeling of modified coir geotextile soil interaction, which the study was carried under the guidance of Dr. Divya PV and with the help of Ms. Sumi Sebastian. Coir is a natural geotextile which is known for its durability and higher tensile strength compared to other natural geotextiles like hemp, jute, sisal, etc. It is composed of lignocellulosic fibers with a lignin content of 40 to 45%, which is responsible for its higher strength and degradation resistance. But natural fibers being inherently hydrophilic in nature, which may cause, like this hydrophilic nature is due to the presence of polar groups, which is responsible for its high porosity and water absorption. So for coir, like natural fibers like coir to be used in reinforcement applications like for coir geotextiles, we have to go for surface modification techniques. And here Saman et al., he has revealed like MMA grafting. That technology using vinyl monomer shows superior tensile strength and photo-oxidative resistance. So after this surface modification technique, we can use coir geotextile for this reinforcement application. As we all know, in a reinforced soil system, the interface acts as the potential weak zone, which may result in progressive failure. Pull-out, like one of the internal stability failures is the pull-out failure, in which the soil, the reinforcement, along with the soil, can pull out of the soil reinforced system. Pull-out force is nothing but the force required to pull the reinforcement out of the reinforced soil layer. And the pull-out resistance, it is the contribution of both interface frictional resistance that is offered by the top and bottom surface of the reinforcement, and the passive resistance offered by the vertical surfaces of vertical surface of the transverse bar of geogrid. As far as geotextile is concerned, the interface friction only provides more, will be dominant in the case of pull-out resistance. Also, pull-out capacity is dependent on the friction factor F star, then vertical effective vertical stress sigma and anchorage length Lg. As of now, there are limited data on modified coir geotextile interaction. So in this study, we have tried to examine the pull-out behavior of modified coir geotextiles in lateritic soil, along with simulating the pull-out of modified coir geotextile using a numerical model. In the present study, we have utilized the soil obtained from Palakkad only, like which is normally using for embankment construction. As per USCS, it is classified as silty sand, and the properties are as follows. A 900 GSM coir geotextile was used for this study with a maximum tensile strength of 17.5 kilonewton per meter, and this was taken for surface modification. Here, it was grafted with a methyl methacrylate. It's a vinyl monomer. The initiator was potassium persulfate. Catalyst used was laboratory reagent grade ferrous ammonium sulfate. So this initiator, potassium persulfate, causes the polymerization of MMA, which later will have the covalent bonding with the MMA and the fibers of coir. So this was taken for, this modified coir geotextile was taken for pull-out testing. Pull-out test was conducted in large pull-out test apparatus, which is in our lab in IIT Palakkad. Here the pull-out box consists of, box is of 1 meter length and 1 meter width with a height of 0.7 meter. Here the front portion of the pull-out box is horizontally divided into two for placing the geotextile. This soil was compacted at maximum dry density and OMC, and it filled in 7 layers with a height of, with a thickness of 100 mm. In the middle, we have placed geotextile as well. Then after that, we have applied a normal force, and after that, pull-out force was applied at a rate of 1 mm per minute. And the readings were recorded using a PC-based DAC system. Coming to the results, as we can see from the graph, the initial modulus of both the modified and unmodified shows similar properties, but for the unmodified, the maximum pull-out load obtained was 11.34 kilonewton per meter and 15.9 kilonewton per meter for a vertical stress of 6 kPa and 25 kPa respectively. Later, it got breakage due to the tensile failure as well. But for modified one, we have got more pull-out force, and no failure was observed up to a displacement of 150 mm. Of course, this MMA grafting has increased the tensile strength and stiffness. Also, this MMA grafting has improved the surface roughness so that it can enhance the soil, interlocking between the soil and the structural integrity. When coming to the numerical modeling, this was carried out in Abacus and FEM-based software. Here, the geometry of coir geotextile and soil was created and assembled. After that, we have to give the material properties, like geotextile was modeled using an elastoplastic constitutive behavior and with 8-noded brick elements. Soil domain was discretized with the 4-noded tetrahedral elements. Boundary conditions were specified, like the vertical boundaries were allowed to translate in the vertical direction, but the base, it is restricted to displacements in all direction. And for the interaction, surface-to-surface contact discretization was carried out, and in order to give the friction, we have adopted column friction model. So coming to the results, generally the experimental, the numerical results agreed to a great extent with the experimental results, and if we check the displacement along position along coir geotextile, we can see like the displacement was different along different parts of the geotextile, and it was higher near the clamp end.
You have last 1 minute.
This is the displacement distribution along the length of the geotextile. We were able to get the tensile stress pattern as well. Coming to the conclusions, MMA grafted coir geotextiles showed around 50% higher pull-out strength than the unmodified one. Their improved durability will make them a strong candidate to replace synthetic geotextiles. Then FEM model, it accurately captured the experimental data, and this can be used for later parametric studies as well. So these are my references, and thank you.
Thank you. Any questions? If there is no questions, thank you, Aarti. Thank you. So the next presentation is on numerical analysis of ordinary and encased granular piles with tire-derived aggregates in soft soils by Dr. Jaipal Jairaj.
So very good evening to one and all present here. This is Dr. Jaipal. Actually, I'm an assistant professor at NIT Jamshedpur. The topic of my presentation is numerical analysis of ordinary and encased granular piles with tire-derived aggregates in soft clays. So the presentation outline will be introduction, sustainable use of tire-derived aggregates, ordinary and encased granular piles, embankments that are resting on granular piles. That is related to numerical modeling, results and some parametric studies, preliminary results and conclusions. So you don't have to introduce ordinary granular piles or stone columns or ordinary granular columns to this august audience. So we normally prefer this kind of foundations in the case of soft clays, preferably for two reasons. One, they act as very strong reinforcements, and secondarily, they act as large drainage elements, accelerating the consolidation phenomena. So there are some limitations that are associated with this ordinary granular piles. You can see that the load capacity primarily depends on the strength of surrounding soft clay. Especially, you'll not be able to form the column when you have the undrained shear strength less than 15 kPa. You have shallow depth of load transfer, closer spacing requirements, and you'll not be able to form the column, and because of which you lose aggregates. You end up in poor quality construction of the columns, and because of which both the functions you'll be able to lose. It's like your column will neither function as a stone column nor as a drainage member. So for that, people introduced the concept of encasing the granular pile using geosynthetic encasements. So you see here, whatever support that is rendered by the soft clay is going to be offered by the geosynthetic encasement. So you can see that. Okay, I think the pointer is not working. I'll just say that you can see the bulge of the column, you can see the lateral confinement that is offered by the soil, minimal, and the geosynthetic encasement that's suffering the confinement. You can see the granular pile that is resting on the firm stratum, and you can see that there are very few attempts that were made to replace the natural aggregates. That's the problem. In fact, when you take ordinary granular piles, especially for soft clays, very soft clays, you have a lot of aggregates that are dumped inside that column, and you possibly don't know whether you are properly forming the column or how much is the amount of aggregates that are getting inside a particular column for a particular diameter and for a volume. So you have a specific type of waste material that is derived out of waste tires, end-of-life tires, ELT. So whatever that you see is the picture that is taken from the California Department of Transportation. They call it as tire-derived aggregates, which encompasses your tire shreds, chips and crumbs. So they are lighter and weight, higher permeability, lower cost materials. You see that you have typically type A size ranging from 75 to 100, type B from 150 to 300. And if you look into ASTM standards, we have three sizes of particle sizes, tire-derived aggregate sizes that are less than 10 mm, 10 to 50, greater than 50. And you can tailor-make all these aggregates to some extent that is required. So you have 1,400 to 2,900 million tires that are dumped as waste. You see here, there are limited literatures that are available that have used these kind of aggregates in granular piles. So recycling is very strongly advised. So you have the applications in embankment fills, retaining walls, backfills, vibration damping, landfill applications. So this utility of tire-derived aggregates is directly targeting the Sustainable Development Goals released in 2015, related to goal number 3, 9, 11, and 12, related to good health, well-being, industrial innovation, infrastructure, sustainable cities, communities, responsible consumption, and production. So I'll get back to this particular slide a little later before I conclude. That's related to the amount of carbon dioxide that is released per linear meter for different types of options that are available for treating the soft clays. So you see here, I've taken the case study that's very well established in the area of geosynthetic and case stone columns by Professor Almeida and group in 2014. You can see the embankment, that's around 5.3 to 5.4 meters height that was constructed in Brazil. So you can see the layers of soft clays reinforced by these encased granular piles. This particular embankment was fully reinforced, fully instrumented with settlement plates, piezometers, inclinometers, total earth pressure cells, radial extensometers. There are in fact quite a lot of information that are mentioned in that particular paper that would take a lot of time, but I'm making it crisp. You can see the biaxial geogrid spread below this embankment with a strength of 2000 kN per meter. So the total depth is around 18 meters, and for which the columns are reinforcing for a length of around 11 meters. It's around 800 mm diameter columns at 2D space, 2.5D spacing. So this is the numerical model. It's axisymmetric numerical model in Plaxis. You can see the embankment, working platform. That's nothing but the granular platform. You can see the granular pile. You can see the soft clay layers zoomed in once. You can see the biaxial geogrid layers just below the embankment. You have layers of soft clays, soft clay type 1, type 2. In between, you have a small sand packet, medium sand packet, resting on, again, a medium sand followed by stiff clay and dense sand. So the idea is like, I thought of replacing some part of granular aggregates with tire-derived aggregates, TDA, for a depth of around 4 times diameter, starting from 0D to 4D, where D is nothing but the diameter of the granular pile. If it is 0D, it means it's a virgin granular pile without any tire-derived aggregates. 2D in the sense, the replacement of the granular aggregates with tire-derived aggregates for a depth of around 2 times diameter, and it was extended up till 4 times diameter. So the mesh sensitivity analysis was conducted, and a fine type mesh was adopted in this particular study. A total interface adherence was adopted, and you can see I've adopted this tire-derived aggregate properties from Tandon et al. With a linear elastic model with gamma of around 6 kN per meter cube and an E value of 16.25 megapascals. So these are all the model parameters that you can see in this particular journal paper. I've used the same model parameters. That's soft soil model parameters for all the soft clays for type 1, type 2, type 3, soft stiff clays, and more Coulomb parameters for the embankment, granular columns, working platform, medium sand, and dense sand. So this study was validated by one more study. That's a very established case study from Malaysia by Professor Tan. That is on the construction of Penchala Toll Highway Plaza project, constructed using 800 mm diameter columns at 3D spacing. You can see the present study with the field data. So I'll keep it simple. So I have taken 3 cases. It's like for virgin granular columns with and without encasement, a 2D depth of replacement of TDA and 4D depth of replacement. You can very well see that when you replace your aggregates with the tire-derived aggregates, I couldn't see much of the difference for some reasons I'll explain. So 1 and 2 in the image indicates the construction stage of that particular embankment, and second stage indicates the consolidation stage. So it was constructed on a stage-wise construction basis for about 60 days. The total time was around 240 days for the entire consolidation to take place. So you can see that 50% lesser settlements for encased granular piles with TDA when compared to that of ordinary granular piles. And you can see that approximately 40% higher excess pore water pressure for ordinary granular piles without encasement. I'll rush. So you could see the performance is okay, even with the tire-derived aggregates for both, for 3 different depths of OD, 0D, 2D, and 4D for encased granular piles. And this is the bulging data. So when you control the properties again with the strength of the geosynthetic encasement, if I give a good quality infill material inside the granular pile with a better friction angle, and if I have a higher tensile modulus of the geosynthetic encasement, my settlements are further reduced. So in that way, I'm advantageous. So the target of this particular, or the whole objective of this particular paper is to address the settlements or the settlement behavior of the composite. So these are all the values. And conclusions. So before I get inside the conclusions, I'll just go to this particular slide for 1 minute. I'll just show. So if you see here, there are plenty of options available for treating the soft clays. This particular literature, Zorer et al. In 2010. This was published even before the release of the Sustainable Development Goals. During the Millennium Development Goals were introduced. You can see that it starts from this board pile of 90 centimeter diameter that ranges from board pile of 90 centimeter to the vibrated stone column with the gravel. So out of all other foundation options, you can see that for vibro stone columns, the amount of carbon dioxide that is released is around 7 to 10 kg of carbon dioxide per linear meter. In fact, this even less than VSE comes your encapsulated granular column. Just 1 minute, sir, I'll just conclude. Even less than this is your encapsulated granular column, and in that granular column, if you are replacing that with tire-derived aggregates, you get a better advantage, or I would say a sustainable advantage when compared to that other conventional practice. So with this, let me conclude. I have given all the data. I have given all the discussions in the presentation itself. So thank you. If you have any queries, I would be happy to interact. Yes, gentlemen.
Just one question.
Yes, gentlemen.
One question, please. A short of time.
Sir, have you come across, like while installations of your piles, have you come across smear zone and clogging of your piles?
Yes, it's a nice question. I addressed this particular question by saying that we have adopted a perfect interface adherence, which means I assume 100% contact with the clay, and it's a mixed layer, right? I have an aggregate on one side, I have the clay on the other side. In between, I have a geogrid. So it is little difficult to quantify the interface of these three layers, but people have done that, and some people in the literature have advised to go for 100% adherence. So I have taken that.
Sorry, thank you. You can actually discuss with Dr. Jaipal later.
Thank you, sir.
Thanks.
Thank you, sir. Thank you.
So the next presentation is on interface shear efficiency of geocell anchor cages by Arya Krishna.
Good evening, everyone. I am Arya Krishna, final year PhD student working under Gali Madhavi Lata at IIC Bangalore. So the topic of my presentation will be interface shear efficiency of geocell anchor cages. So we know that geocells are three-dimensional cellular confinement systems which are extensively used in various geotechnical applications like foundations, pavements, retaining walls, and slope protection, erosion control for the past 50 years, more than 50 years. Even though geocells have undergone several transformations geometrically in terms of its shape, configuration, texture, connections, etc., the fundamental structure of the geocell always remained the same with interconnected cell and infill soil. So recently we have tried structurally modifying the geocells using an anchor cage system in which each geocell will have an anchor pin at its center, and these pins are connected to a grid to form a cage-like structure. This is a schematic representation of how a geocell anchor cage will be, and the anchor cage can be placed above or below the geocells depending upon the requirements. So as a preliminary step, we have conducted foundation model studies on geocell foundations and geocell GAC foundations, and we have found out that the inclusion of GAC within the geocells has improved the bearing capacity and reduced the deformations. We all know that the shear strength mobilization at the sand geosynthetic interface is the governing factor for any geosynthetic reinforced soil structures. Since GAC is a very novel technique, we have to explore the interface shear characteristics that is present at the interface of geocell GAC sands. So the main aim of my study is to quantify the interface shear mechanisms of geocell GAC sands relative to the conventional reinforcements such as geocell and geocell grid combinations. So in this study, since GAC is a very novel technique, it is brought into practical reality using 3D printing technology. And this is the FDM printer, fused deposition modeling printer, that is available in our lab, which works on liquefied polymerization technique, which involves the continuous melting and bonding of the polymeric filament. And PLA, polylactic acid, is used to fabricate the GAC model. And here the geocells are also fabricated using a 3D printing technology. This is because the commercial geocells always come with prefix dimensions, texture, and configuration, which is not always feasible for small-scale experiments. So here we have fabricated geocells from the ultrasonic welding of 3D printed PP sheets. And previous studies on these 3D printed geocells shows that they could replicate the actual confinement and beam effects offered by those prototype geocells. So coming to the interface shear test, this is the schematics of the large interface shear setup that is available in our lab. And we have conducted experiments, 4 different set of experiments. First one is sand-to-sand interface test, sand geocell interface test, sand geocell grid interface test, and sand geocell GAC interface test. In all these tests, reinforcements were placed in the lower shear box for maximum interface interactions, and sand is placed in the upper shear box. And locally available river sand was used, and the properties of the sand and microscopic image is also provided here. And this is how the reinforcements are placed in different lower shear boxes. All the specimens were manually compacted to achieve a relative density of 70% and sheared at a strain rate of 1.25 mm per minute until the lower box moved 20 mm horizontally for 3 different normal stresses of 25, 50, and 100 kPa. Then coming to the shear displacement plots, we have observed that all the geosynthetic interfaces have improved shear strength compared to the sand-alone interfaces. And among the geosynthetic interfaces, GAC has better shear strength compared to geocell alone and geocell grid combinations. And we have computed in the terms of interface efficiency at both peak stress and residual stress. Interface efficiency is the shear stress mobilized in the reinforced specimen to that corresponding in the unreinforced specimen. And even at residual state, an interface efficiency greater than 1 is observed. Then coming to the failure envelope, that is Morse-Coulomb failure envelope is drawn for different cases, and the shear strength parameters are quantified here. We have seen that in all the cases, an apparent cohesion is mobilized, and a greater cohesion is mobilized in the case of GAC, which is about 1.6 times greater than GR interface and 1.4 times greater than GAGR interface. And dilation angles were also quantified from vertical displacement, horizontal displacement plots. So coming to the various shear mechanisms at various sand geosynthetic interface, and this here we will be quantifying in terms of frictional resistance and passive resistance mobilization. In the case of sand geocell interface, there are basically 3 interactions. One is frictional resistance from sand to sand interactions, frictional resistance between sand and geocell protrusions available at the interface, and also passive resistance mobilized due to sliding and rolling of sand particles over the geocell protrusions available at the interface. Since the area of geocell protrusions available at the interface is very less compared to the sand, the frictional contribution from sand geocell inclusions can be completely omitted, and it is usually omitted in almost all the studies. And when coming to sand geocell grid interface, we have, in addition to those interactions that is available at sand geocell interface, we have contribution from grid, which includes sand grid frictional resistance and also passive resistance due to sliding and rolling of sand particles along the transverse and longitudinal ribs of the grid. And coming to sand geocell GAC interface, here we have contributions. In addition to all the contributions that is available at sand geocell grid interface, we have contributions from pin, which are perpendicular to the direction of the shear and connected to the overlying grid. So the passive resistance mobilized due to the interactions of the pin, which is available in the vicinity of the interface, provides an additional passive resistance in the case of SAN geocell GAC interface. Since passive resistance is a direct measure of the adhesion, compared to the geocell interface, the adhesion is improved in the case of GAC interface due to the additional contributions of passive resistance from the pin and the grid. So to quantify the micro, or to visualize the micro mechanisms and particle interface mechanisms, we have conducted particle image velocimetry analysis, and it is conducted using PIV toolbox that is available in MATLAB. And during the interface test, we have captured high resolution videos using Olympus camera, and these are the PIV plots that is obtained for various SAN geosynthetic interfaces at 25 kPa, and we have found out that GAC is having greater interface interactions, followed by GGR interface and the least in GR interface. And also we have found out that the maximum dilation is observed in the GAC interface, which is matching well with the experimental results. Then shear zone analysis is also conducted. Shear zone analysis is defined as the depth of the box over or height of the box over which there is a change in the velocities, or change in the velocities of two different boxes. That is the change in the velocity between the upper and lower shear boxes. And the shear zone is a direct measure of interface shear mechanisms, and a greater shear zone thickness usually indicates a higher shear strength mobilization. And the shear zone thickness for various SAN geosynthetic interfaces at different normal stresses were computed, and found out that the GAC is having higher shear zone thickness compared to GGR and GR interface at all different normal stresses. Then coming to the beneficial effects of geocell GAC over geocells, and we have for that, for practical applications, we have done experiments on geocells and geocell GAC interfaces for 3 different pocket sizes of geocells: 75 mm, 100 mm, and 150 mm. And these are the quantity of material that is invested for all of these tests. And interestingly, we have found out that the GAC with 150 mm pocket size is able to provide the same shear strength as that of GR with 75 mm pocket size. And on coming to the material, like look at the material used, it is like for GR75, we will be investing about double times that of a GAC 150. So for a design purposes, the inclusion, or as a designer, they can use geocells and inclusion of geocells with inclusion of anchor cages in geocells with higher pocket sizes instead of geocell Elon with 75 mm or half the pocket size with much lesser cost. So coming to the conclusions, and geocell GAC interfaces is always having better shear strength characteristics compared to geocell and geocell grid Elon. The interface addition mobilized is about 1.6 times, which is greater than geocell interfaces, and 1.4 times higher than geocell grid interfaces. And a greater shear zone thickness is observed in GAC interface compared to geocell and geocell grid combinations. And the addition of anchor cage to geocells of larger pocket size of 150 mm helps in mobilizing shear strength equivalent to the system with geocells of half the pocket size with much lesser cost. This is all about.
Thank you. Any questions? Thank you. The next presentation is micromechanical insights into frictional behavior at non-dilative geomaterial interfaces by Dr. Lalit Kanpal.
Yeah, good evening everyone. And so the title of my presentation today is Micromechanical Insights into Frictional Behavior at Non-Dilative Geomaterial Interfaces. So it's a long title. And this work was done by me in IIT Delhi when I was a PhD candidate. And then, yeah, so currently we are exploring the micromechanics for the granular material, and this was done for the geomaterial interfaces. So
Like interface, we already know it's a plane where two different material interacts, and we encounter different types of interfaces in our studies, like skin friction piles, reinforced slopes, or landfill liners, and then anchor systems and all those. So we have different types of interfaces, and coming to the types of interfaces based on the soil particle size, we can classify them into two different types. One is dilative, the other non-dilative interface systems. Yeah, for the dilative interface system, the particle size is small with respect to the asperities, and thus the load transfer is due to several mechanisms, which includes friction, interlocking, dilation, and all. Whereas in the case of non-dilative interface system, the load is transferred only through friction, and thus these are the most now we can see, like in the case of dilative interface system, there's significant volume change, and then interface shear strength is either equal to or greater than the soil shear strength, whereas in the case of non-dilative interface system, little internal soil resistance is being mobilized, and thus these behavior cannot be described using the traditional soil mechanics concepts, and these are one of the weakest and complex planes. So my PhD work was based on the non-dilative interface system. And then, like I described, the load transfer in the case of non-dilative interfaces is majorly through friction. So these are defined as friction-dependent systems. And in the geotechnical structures, or whether in situ characterization devices, we can characterize. So in geotechnical structures, so in the case of geotechnical structures, it's like soil geosynthetics. Like in the case of landfill liners, we can see the interaction between the landfill liner and sand behaves as a non-dilative interface systems, where, as also in the case of skin friction piles, the load transfer from the structure to the surrounding soil is again majorly through friction. And then coming to the in situ characterization devices such as CPT, self-burrowing probes, the characterization depends majorly again on the response of the frictional behavior between the instrument and the surrounding soil. So coming to this picture, then like why do we need these studies? So like we have already said by the early work of Coulomb and Amundsen, so since the work was majorly micromechanics, so we have seen that the frictional laws were already given. However, they are valid for metals and only for certain load range only. And then came further many studies where they have said that many materials do not obey Amundsen's law, as their friction coefficients can vary with the normal load. And this is one of the typical response given by Dove and Frost 1999, where we could see so we could see the frictional coefficient either initially decreases and then increases, and the change in the frictional mechanism occurs at a critical normal stress. So keeping in mind, then we have said like how the frictional response varies. So coming to the behavior of the interface system, it depends on the behavior of the soil as well as the continuum material. So coming to the soil, it depends on the shape of the particles, grain size distribution, density, saturation. And for continuum material, it depends on the surface roughness and hardness of the continuum material for the non-dilative interface system. So then we did the literature review, and we have several papers on this where they have studied the different factors with different significance level they have given. So there are several papers in the literature where they have done macro level interface shear test to characterize the interface shear response, but till date no studies are available in literature in geotribological framework to understand the fundamental mechanism from particle level testing. So then coming, like, since we have already studied about the geotribology, so like this is a very famous quote. And then coming to geotribology, it's a word made with two words, geomechanics and tribology. So where we study of the mechanics of soil, and tribology is the branch of mechanical engineering where we study friction, wear, and lubrication. So the principle of tribology can be extended to geotechnical systems and can provide insight into shear strength behavior of non-directives. So keeping that in mind, we have kept our experimental program where we have used a multifunction tribometer to perform the shear response test, and this is the final testing configuration. So yeah, we can attach our single particle to the collate system, and we share that particle with respect to the interface, and we can compute single particle friction coefficient using this. And then this is the apparatus used, and then these are the material used. So for this study, we have used glass beads, and then we have used two different continuum material. One is stainless steel, and the other is geomembrane. The samples were kept circular, and the edges of the samples were nulled so that there's no friction between the other components of the system. Using these tribo pairs, we have used different testing conditions. So normal load we have done for 5 different types of normal loads with displacement range varying from 0.5 to 16 meter and number of revolutions 6. So this is again one of the typical shear surface which we have shared, and we could see like whenever the particles are sharing in the sharing direction, there are certain particles which are exposed to prior shared surface. So keeping that thing in mind, the circular sharing always helps us to get some better idea about the structure, about the interface shear response. So we have used 6 number of revolutions for that case, and the number of particles tested for each condition in this case is 6. And then results and discussion. Since it's a micromechanical interface shear test, we have used single particles. So I have just given the force response. The force response remains constant throughout the test just to ensure that there's no force fluctuation during the test happening for the single particle, and which may influence our shear response significantly. So just to ensure that I have given the normal force with number of revolutions, and then coming to the shear force versus number of revolutions, like how the shear force is fluctuating with the number of revolutions. So this is for 2 different interfaces. Like I said, the GBGM, GBST, GBGM geomembrane, and then stainless steel. So we could see the geomembrane is a flexible continuum material, whereas steel is a rigid material, metallic continuum material. So in the case of geomembrane, we could see it's initially decreasing and then again increasing due to the surface deformations, whereas in the case of stainless steel, it decreases and then it becomes somewhat constant. So the effect of number of revolutions was studied in this case, and then we have plotted the coefficient of friction versus normal load for the different cases, GBST and GBGM. Yeah, the friction coefficient was the surface roughness of both the continuum material were kept same in order to ensure to isolate the effect of hardness of the continuum material. So we could see the friction coefficient was higher for the case of GBGM due to the softer continuum material, resulting in the resulting in the better contact asperities in contact. And then coming to the coefficient of friction with the displacement rate, since we have done it for till 16 mm, so we could see the coefficient of friction initially didn't decrease much, but then at the higher displacement rate, it again started decreasing much significantly due to the no junctions being formed between the particle, or like not having sufficient time for the asperity junction to form during shearing. Yeah, so this was the test, and then yeah, basic conclusions. Yeah, shear force increases as we can see in the case of macro shear test. We do find like here also it increases with the more pronounced frictional response for the softer geomembrane, again due to the better contact between the softer continuum materials. And then surface damage over the time causes the shear force or GM to gradually increase after initial remaining constant, and whereas in the ST it first decreases and then stabilizes over the time. And then COF increases with normal load, with GBGM generally exhibiting a higher CO than GBST, again for the coefficient of friction. And then the displacement rate was studied for this case, where we could find higher rates leading to reduction in COF due to limited time for asperity junctions to form. That's it. Thank you, everyone.
Thank you. So thank you, Kanpal. Due to the paucity of time, we will move on to the next presentation. Next presentation is on influence of spread ratio of overlapping geogrids on pull-out resistant factors and shear parameters by Osman.
Good evening, professors, attendants. My name is Usman. I am a PhD student from IIT Hyderabad. Today I want to present my master research work. And my research title is Influence of Spirit Ratio of Overlapping Dew Grade on Pull-out Resistance Factor and Shear Parameters. We know that in MSC walls, one of the very important components of internal stability of MSC walls is the interaction between field soils and reinforced materials. So I will go, firstly I will not open these basic things. And this interaction between field soils and reinforced materials governing by soil density and dew grade geometry and dew grade roughness surface and normal stresses. And this interaction are commonly evaluated by pull-out and direct shear testing. According to ASTM standards, in pull-out and direct shear testing, we place it only one layer of dew grade or any type of reinforcement within the soil specimen and subjected to pull-out or shear load to evaluate the pull-out or shear resistance. But in the field, engineers sometimes, instead of using one layer of dew grade, they have to use different dew grade configurations by using two layers of dew grade by overlapping them and spread them in trapezoidal shape. So from there, our objectives came to simulate the dew grade configuration engineers using in the field in the laboratory and to evaluate the effect of spirit ratio of dew grade on the pull-out and shear behavior. To do that, to simulate what people doing in the field in the laboratory, we set two layers of dew grade by overlapping them in pull-out and direct shear boxes, and then we set them in a rectangular shape, and its area is A, as shown in the first picture, and then we fix one side and spread the other side to make the trapezoidal shape, and its area is A star as showing in picture 2. And from there, we have introduced new parameter, spirit ratio SR, and it equal to A star by A, where A star is the area of dew grade after spreading, and A is area of rectangular dew grade before spreading. To do the comparison, we have testing 3 different dew grade arrangement, one single layer of dew grade as recommended by ASTM standards, and then SR equal to 1.3 and SR equal to 1.6. There are 3 samples or specimens we have testing to do the comparison. Material use we have using Indian standard sand, call it inert sand, and polyester uniaxial dew grade with these properties, and achieved density density was 80.3%. Let's come to our result. In pull-out testing, the pull-out resistance was increasing with the spirit ratio, where dew grade with 1.6 spirit ratio was record the higher pull-out resistance, showing by the red color under all the normal stresses, and then G grade with spirit ratio 1.3, while one single layer of G grade achieves the lower spirit ratio, achieves the lower pull-out resistance. Also, we calculated the pull-out resistance factor, the same result. G grade with spirit ratio of 1.6 achieves the higher results, and then G grade with spirit ratio equal to 1.3, and then single layer of G grade. Enhancement in pull-out resistance factor of 30 to 64%, achieve it when SR equal to 1.3, and 35 to 69% were achieved when SR equal to 1.6. The mechanism of this behavior is, we know that the interaction between soil and G grade depend on the friction resistance between soil and G grade surface, and passive resistance against the transference ribs, and the soil interlocking in the G grade pictures. So when we increase the spirit ratio, that means we increase the friction area, and we increase the passive resistance, or we increase the transference ribs, and also we increase the interlocking apertures. So that will affect in overall pull-out resistance. In direct shear test, the result was reverse to pull-out resistance. So the shear stress was decreasing with the spirit ratio, where G grade sample with single layer G grade achieved the higher shear stress or shear strength, and followed by G grade with SR equal to 1.3, while G grade with SR equal to 1.6 achieves the lowest shear strength. Same thing in the shear envelope also. G grade or sample with single layer of G grade was achieved the higher, and then followed by SR equal to 1.3, and then SR equal to 1.6. And reduction in the peak shear stress was observed up to 5% for SR equal to 1.3, and up to 8% for SR equal to 1.6. Also, we have calculated the interface shear strain coefficient alpha, and it equal to shear strain of soil G grade by shear strain of soil. Same thing was happened. Single layer of G grade achieves the higher interface shear strength, and then followed by SR equal to 1.3, and then SR equal to 1.6. And the mechanism of this is all researchers are reported that G grade in pull-out or G grade in direct shear test act as a smooth surface, help soil particle for sliding. So when we increase the spirit ratio, that means we increase the smooth surface, and it will affect our shear behaviors. Our conclusion from that, a novel parameter, the spirit ratio, was introduced in this research. And higher spirit ratio reduces the peak shear stress up to 5% drop at SR equal to 1.3, and 8% at SR equal to 1.6, and that is negative effect. And for pull-out resistance, increase in spirit ratio, increasing the spirit ratio significant enhance the pull-out resistance factor, where 30% to 69% improvement in the pull-out resistance factor, and that is positive effect. Finally, I would like to thank Indian ICCR, which was supporting my master's degree, and now IIT Hyderabad supporting my PhD research through the Ferris Fellowship Program. I gratefully acknowledge this financial support. Thank you.
Thank you, Osman. So I think we'll have the question and session later due to paucity of time. Thank you, Osman. So the next presentation is design and construction of two-tiered polymeric strip reinforced soil wall by Rudra.
Very good evening, everyone. I understand that we are in Goa and it's already 6:45, so I'll be as brief as possible.
Thank you.
Yeah. So I'll be presenting a case study related to design and construction of a two-tiered polymeric reinforced strip wall. I'll not get too much into details, but here I would highlight a few things. Of course, this is a schematic diagram showing different components of a reinforced soil structure. But there are a few elements which we need to be mindful about, especially related to the connection between the reinforcing elements and the fascia, and also the drainage bay provisions. Of course, as you might all be knowing, there are different shapes of panels available with different types of architectural finishes that are possible. So it can lead to a very beautiful structure if done properly. For this particular project, we have used ParaWeb, which is a polymeric strip reinforcement. Basically comprising of tendons made up of the high tenacity polyester yarns encased in polyethylene sheath. Okay? And of course, these are certified products. For the project, yes, the client is NHAI. The consultant for this project was RV Associates, a contractor L&T, and we were the technology provider. So we are talking about a project in Gujarat. It's a part of the ambitious Delhi-Mumbai Expressway. So this particular, let's say, section that I'm going to refer to is Vadodara-Kim section, and in that specifically the ROB at Chennai is 373 plus 589. This is the plan drawing of this particular location of the ROB. On the A1 side, we need the two-tier structure because here in this case the maximum height is a whopping 9.2 meters. And on A2 side, the maximum height is 14.4, and hence it is designed as a single tier structure. Interestingly, of course, on the A1 side, if you can see, there's a culvert also passing below the wall, so which makes it a little tricky. Of course, we had to provide the slip joints and everything to ensure that the structure remains safe. I'll not spend too much time into this. Of course, the designs have been done for the ultimate limit state, serviceability state, internal checks, external stability checks, and with respect to the soil properties, these are the properties. The fill, which was used as reinforced fill, was definitely good. And retained fill did have lower fire value and cohesion as well. As per the Warlock, sandy layers were present up to depth of 4.5 meters, followed by low and medium plastic clay. So yes, we had to carry out a proper consolidation check apart from bearing capacity. And a replacement of around 2 meters was done as a shallow ground improvement scheme. In terms of loads, the traffic load was 26.4 kPa, dead load 13.5, crash barrier friction slab load adopted was 8 kPa, and interestingly, there was sleeper slab as well, which had pressure of 120 kPa that was coming on the structure. This sleeper slab is basically the slab which you can see in the sketch below, which is of 1.5 meters width, and the approach slab is sitting on it. So we had to account for that load in the design of the cross wall as well as the longitudinal wall up to 0.5 times the height. This is the overall scheme, how it looks like. The carriageway is quite big because it's an 8-lane road. Here we are talking about, since we're talking about 19.2 meters height, we had to provide a berm of 0.8 meters width. Again, there were ROW constraints because of which we were not able to provide it for typical 1.5 meter which is required. But yes, the upper tier height was maintained at 7.2 and the lower tier height varied from 7.2 to 12 meters depending on the ground profile variations. One very important aspect with respect to design for this particular project was that if we follow the codal guidelines, there was a case in A1 side wherein when the total height is more than 16 meters, berm width, if the berm width is less than 1 by 20 of H1 plus H2, the wall needs to be designed as a single structure, full height. It cannot be bifurcated into 2 tiers. And while case 2 is a situation wherein The berm width is between h1 plus h2 by 20 and less than or equal to h2 10 5 45 minus 5 by 2. In this case, we have to adopt the tension maximum tension line as per the diagram which is given. So this is something is a small nitty-gritty which we need to be mindful about when we are dealing with such multi-tier structures. Some construction photos, yes, these are some of the photos of the wall under construction. You can see the installation of para-web strips, soil compaction being carried out. You can see it's a very, very wide embankment. And these are some of the photographs of the completed structure wherein you can see the two-tiered cross wall as well as longitudinal wall and the overview. Okay, coming to conclusions. Two-tiered RS wall, of course, of such heights has been successfully completed in a span of 6 months. This was completed in 2022, March, and has been doing well since then. Design of such structures definitely requires due diligence and proper investigation apart from just the design. Importantly, the closing walls at abutment need to be designed to cater to additional loads, like for example, sleeper slabs or pedestals, as and when they are present. And such structures have definitely proven to be very, very effective, owing to its flexibility and speed of construction. So that's it. With this, I present my case study. Thank you very much. And if there are any questions, we can discuss, or we can go to the next presentation also, which I'll be doing. Oh, okay. Yes. Go ahead. Okay. Can you please load the second presentation? So while the presentation is loaded, I'll be presenting on behalf of my colleagues. One of my colleague is from Nepal. He is not here, unfortunately, so I'm presenting. And then there are two professors, which of course are, one is from Nepal and one is from US. So we have seen now where we were in the plains. Now we will go to the mountains of Nepal, where there's an interesting case study related to slope stabilization done for a penstock for a hydropower project. So here we go, it's loaded now. So we are talking about a project called Middle Tamar hydropower project in Nepal, wherein there was a critical slope failure that happened once the excavation was done. The height of slope is 80 meters on which the penstock need to be installed. Okay, the slope comprised of coarse-grained soil, and there was also the water outlets flowing along the slope, making it very, very critical. And then, of course, there was constant monsoon exposure. There was tunnel muck deposition done on the slope, which made it very, very loose and unstable. The critical factors for this project were, number one, yes, the steep slope, the unconsolidated covalent deposit, heavy monsoon rainfall. Toe excavation was being carried out for the powerhouse construction, and then the muck was disposed on the slope. In terms of the location, we are talking about this project is in the northeastern corner of the country in Nepal. And the original terrain comprised of agricultural land with a gentle 45-degree inclination, mainly comprising of the colloidal residue which was there. There were no recent landslide activity until the construction began in 2017. Here in the photograph below, you can see the slope geometry and the alignment of the penstock, wherein we had anchor block at the top, at the bottom, and then the powerhouse excavation is going on, and the yellow line is showing the penstock alignment. So this is the scheme of the project. The penstock pipe is structurally supported by 2 anchor blocks and a saddle slab. The anchor block at the crest, marked in orange, is founded on bedrock after doing necessary excavation, while the anchor block at the toe is founded on soil after carrying out necessary ground improvement. So in terms of the slope failure that happened when they were doing the trimming, since there was a lot of tunnel muck deposition that compounded the problems, there was monsoon, which again compounded the problems, excavation was being carried out, and everything led to a deformation of the excavated slope. Of course, there was a lot of investigations carried out. The soil composition characteristics was found using the ERT, plus doing the boreholes and doing the lab tests. As you can see, the cohesion is negligible, just 1 kPa max, and friction angle is also low. Maybe it's because of the poor grading of the material that was there. So the solution that was adopted was comprising of Paralink 200 geogrid, its highest strength geogrid, and it was installed at every 1 meter interval. Then at the face, there was a plumb concrete done to retain the fill, and then on top of it, the penstock was constructed. The key advantage of this solution was that it expedited the construction schedule, and it was quite comparable and more, let's say, economical than the conventional structures. In terms of construction methodology, this is how it was done. First, the removal of sliding mass was carried out. As you can see now, the slope is now completely cleaned up of all the loose deposits. This was followed by, again, a survey and investigation so that we are sure what we are dealing with. Then the geogrid installation was done in layers, which unfortunately is not so clearly visible, but then there are CN lines at very 1 meter interval with a wraparound at the face, okay? And at the interface between the in-situ strata and the reinforced fill zone, there is a MAC drain geocomposite to allow for the drainage, acting as a chimney drain essentially. And on the face, we have the plumb concreting done, which acts as a saddle for the penstock pipe ultimately. The design was carried out using GeoSlope software, and all the checks were done for different stages of construction. First, of course, starting after the excavation was carried out of the loose soil, then when the reinforced soil structure was completed up to mid height, what was the factor safety, followed by the full construction of the reinforced soil structure, and then the D is the one wherein the pipe is also installed, okay? And then, yes, the static and seismic analysis were definitely carried out. And the confidence of going with this solution started with a case study in Lower Likhu hydropower project, wherein a similar reinforced soil structure was implemented for a 40-meter high penstock slope above the road. This was completed in 2020, and we have seen in recent times how monsoons are, getting worse and worse. So this has been able to bear the brunt of, very disruptive monsoon seasons across few years, and has been delivering well. And that gave the confidence for adopting this for even a 80-meter high slope. This is how it looks like in terms of completed photographs. You can see the penstock is completely installed, and the project is functioning. In terms of conclusions and recommendations, yes, the critical success factors were, it was essential that we remove the sliding mass, which was loose. High strength geogrids are effective for steep slopes. Drainage is something which we should not miss out for any reason whatsoever. And such systems can allow for the simultaneous construction, saving significant time. In terms of recommendations, we should avoid disposing the muck on such slopes, for sure. We can consider geogrid reinforcement for such application areas, implement drainage, and yes, it is very important to do stage-wise numerical verification so that we are sure that at all stages of construction we are safe. So yes, the successful stabilization of this slope demonstrates that the geogrid reinforcement does offer an economical, time-efficient solution for challenging hydropower projects. That's it from my side. Thank you very much.
It's really wonderful work. We should appreciate, because there is no audience, but I really salute you for such a wonderful work. It's really, as a civil engineer in general, as in geotechnical engineer in particular, taking up such wonderful works. I really appreciate McAferry and your team. Thank you. Thank you very much.
Thank you. So the last presentation for this particular session is on design curves for preloading nonlinear consolidation with vertical drainage.
Good evening to one and all present here. Myself, Krawoklang Karsimyong, a research scholar at IIT Roorkee. Okay, sir. Good evening to one and all present here. Myself, Kraboklang Khasimyong, a research scholar at IIT Roorkee. And today I'm going to present on design curves for preloading nonlinear consolidation with vertical drains. And these are the contents of my study. So first of all, we'll look into the challenges for soft soil, like when we do any constructions on soft soil. Infrastructure such as ports, roads, buildings encounters such difficulties when building on soft soil. And as we all know that soft soil has low bearing capacity, as a few colleagues have already presented about soft soil. So it has high compressibility and low permeability, which complicates for construction purpose. And there are many ground improvement techniques to improve such type of soil. So we have sand drains, we have stone columns, we have also piles foundations as they already presented. But here in my case, we are considering PVDs for to improve the soft soil. So yeah, it's because it's low cost and is for installations. And yeah, this is the figures how they install the PVDs into the ground, and then they surcharge, and then to analyze for analytical modeling, they consider a single drains, and then with that drains, when the drain is installed into the ground, it forms the smear zone where the soil properties got disturbed, and then beyond that there is a zone where the soil it's not disturbed, and as now we move to the nonlinear soil properties during consolidation. So Lekha et al. 2003, he's proposed these two equations that means that explain the changes of void ratios with the corresponding to the applied stress, and also the changes of void ratios with the changes of the permeability also changes, and then void ratio simultaneously the void ratio changes. And these are the terms for these equations. And this is the example by Indraratna 2005. They have done the simple tests, laboratory tests, and they have found that the CC means the compression index to be 0.229, and the permeability change index, it defines the slope of the permeability during consolidation, and they have found out to be 0.45. So here, these equations I have taken from Indraratna 2005. So in equation 3, you can see the spacing where it deals with the n value and dw, and n is dE by dw, and then to decide the spacings, you have to calculate the degree of consolidation. Degree of consolidation, it deals with the factors such as the applied loading, the time factor, and the factor mu. Where the factor mu, it deals with n, s is the smear zone size ratio, ds by dw, and then a we have defined as th by mu, where th is the time factor during horizontal consolidation, and c is cc by ck is the ratio, where they have considered to be a range of 0.5 to 2. And then B, we have taken to be like considered to be 0.1 to 20, where it can cover all the possible values like field values. And if you see from that equation 5, where it's UH, it depends on A, B, and C. So when we plot to that A, B, and C, and then UH, we have found this design curves. And this is the main curves for this research, and then for different C value. And these curves has been published by myself, and to find out the factor mu. and for different n, s, and k value. And yeah, so this is the design steps. You have to give the input parameters. Once you get the input parameters, you can calculate TH. TH is CH T by D square. And B is the applied load by the initial effective stress. And C is CC by CK. Once you obtain that, and then you go to that graph where UH is equal to, it depends on A, B, and C. And then you'll get the A value. Once you get the A value, and you can calculate the mu value, where mu is equal to TH by A. Once you get the mu value, you go back to these curves. Once you get the mu value, and you also have the NS and K value, you can, oh, no, I mean like, you have the S value, you can calculate N. Once you have that N value, this design spacing can be, I mean, you can extract the design spacings. So you can decide in the field spacing, how much is the spacing between the drains. So this is the design example. So they have performed this example. I mean, this example is taken from the laboratory test. So they have considered only one drain. So here, I mean, I have not calculated the spacing because they have not given whether it's a triangular or square spacing patterns. So we have, because they have considered only one, so there is no patterns of the drains. So we have calculated only the N value, where we found out to be, from the design curves, we obtained out to be 7.24 if you see in the step 4. And then as per Indraratna 2005, they have found out to be 6.79, where I mean, the error is 6.63. So we can say that it's the design curves is like accurate enough like to judge the, I mean, compared to the laboratory test. And yeah, for future scope, like we can also go for large strain where they, because this model we have considered only for small strain where the change in the, I mean, the settlements is not much as compared to the total settlement. So we can go for the large strain, and also we can consider the well resistance. So this is the conclusions that we have proposed these design curves, and then further also for recommendations also has been proposed. So these are the references, and thank you.
Thank you very much. So we are almost at the end, left with only few people. Really appreciate your sincerity. And really it was a nice session. I just want to say one thing. It's a mixture of academic and industry, frankly speaking. And the two go together just like wife and husband. And I really appreciate the great works that were presented here, which are marvelous, really. Thank you very much. And of course, I should appreciate Ramesh. He's very sincere. He says 9 minutes dena hai, and 1 or 2 questions should be there. Good, sir. Thank you.
Before ending the session, I would like to request Dola ma'am to hand over the memento to our chair and co-chair. Thank you, everyone. Now we formally close the session.